I'm sorry I can't be with you at the conference today. Thank you for letting me show you this video version of my talk. The no-go result pertains to an assumption routinely made in the thermodynamics of computation. It is that when we work at molecular scales, we can chain together many thermodynamically reversible computational processes so that overall the total amount of entropy created by them can be made minimal. The processes at issue are indicated here. They include compression and expansion of component spaces, detections of memory device spaces, moving data from one location to another, and more. The no-go result asserts that thermal fluctuations, or noise, prevent completion of any individual molecular scale step. Rather, thermodynamic entropy must be created to complete each step. The amount of entropy created is shown in the formula. It is related to the logarithm of the odds of successful completion of the step. That's the quantity O fin. What this means is that the minimum amount of entropy creation in the thermodynamics of computation is not set by the logical specification of the computation, but by the number of steps that are chained together in order to implement the computation. To get started, I'll give some very simple illustrations of how thermal fluctuations confound our expectations of how molecular scale processes will behave. Take the reversible isothermal expansion or compression of a single component system. Here's a one-molecule gas confined to a cylinder. It is held in by a piston that is weighted by exactly the right amount to counteract the upward pressure of the gas. To allow the expansion to proceed, we reduce the mass on the piston minutely so that the pressure of the gas is just very slightly greater than the restraining weight of the piston. As a result, the piston slowly and gently rises. Throughout the process, we are in near perfect equilibrium. Attaining that equilibrium is the essential thing. The closer we get to that equilibrium, the slower the process proceeds and the less entropy we create. As the expansion proceeds, the temperature of the gas drops minutely, so heat is passed in very small increments into the gas and is then recovered as work. The amount of heat passed is kT log 2, that is 0.69 kT. While the gas expands, its pressure is dropping. That means we have to constantly adjust the mass m of the piston in order to keep the entire process in perfect balance. For a given mass m, perfect equilibrium is attained when the piston is exactly at the height given in the formula HEQ, that is kT on mg. This is an important formula for this case, and we will come back to it shortly. This then is what we expect, a process in which the pressure of the gas is balanced perfectly by the weight of the piston. The expansion proceeds arbitrarily slowly, inexorably over increasing periods of time so that we can render the total amount of entropy created as small as we like. Now comes the complication. If the process is to proceed as intended, the piston must be very light. For collisions with a single molecule must be sufficient to lift it. But the piston is itself a thermal system and will have its own thermal energy. And if it is very light, that thermal energy will scatter it throughout the volume of the cylinder. More precisely, the fact that the piston is a thermal system in its own right means that it will be Boltzmann distributed over the height of the cylinder. The mean of the distribution turns out to be the same equilibrium height that we saw earlier, More seriously, the standard deviation of the distribution turns out to be that same equilibrium height. That means that the thermal character of the piston itself is scattering it throughout the full height of the cylinder. This is what it does quite independently of any collisions with a molecule. This then is what really happens when we try and carry out a reversible isothermal expansion of a one-molecule gas. The piston is not waiting for collisions from that one molecule to lift it up. It already has its own thermal motions that are flinging it all the way through the full expanse of the cylinder. There is no definite beginning and no definite end to the process. What about the slow passage of heat to the gas in tiny increments? The same problem appears. Thermal fluctuations lead to energies that rapidly surge backwards and forwards and obliterate the slow transfer of heat intended in the process. More precisely, the mere fact that the one-molecule gas is a thermal system means that its energy is Boltzmann distributed. It will have a mean energy of 3/2 kT if it's a monatomic gas, and a standard deviation of 1.225 kT. This standard deviation reflects wild fluctuations in the energy of the gas that will completely swamp the tiny amount of heat that we expect to pass in the isothermal expansion. That tiny amount is merely 0.69 kT. An awkwardness of this arrangement is the need to adjust the mass of the piston constantly in order to keep it in balance with the gas pressure. This external intervention can be avoided if we adjust the external field appropriately. I have described elsewhere how this can be done. Exactly the same problem arises when we try to set up systems that can measure or detect the state of other systems at molecular scales. Here are two such systems that have been proposed in the literature. This device is intended to detect which side of a two-chambered vessel contains a single molecule. The keel-shaped frame is gently lowered onto the molecule and is slowly tipped by the pressure of the single molecule gas. Here's another process in which a dipole is slowly coupled to a data bit contained in another dipole in order to read the dipole state. Thermodynamically, a reversible detection process is the same as a reversible compression of a one-molecule gas. In its ready state, the detector occupies the full volume of its available configuration space. In the detection process, the detector's space is reversibly compressed to that portion that represents the result intended. As with the one-molecule gas compression, the process is intended to proceed arbitrarily slowly with the driver in perfect equilibrium with the target device. This is how we expect the process to proceed. The little man is the analog of the mass pressing on the piston of the one-molecule gas. The no-go result shows that this process will be disrupted by thermal fluctuations in just the same way as the isothermal expansion and compression of a one-molecule gas. Now let's turn to the no-go result itself. We'll need some preparatory notions in order to set it up. We'll consider the thermodynamically reversible process that happens in the interaction of two thermal systems that are embedded in a larger thermal environment at temperature T. The two systems can exchange heat and work with one another, but they can only exchange heat with the surrounding environment. The condition of thermodynamic reversibility is that all thermodynamic forces are in perfect balance or minutely removed from them. That means that a thermodynamically reversible process consists of a sequence of equilibrium states. We arrive at a quantitative expression by introducing the standard thermodynamic quantities shown here. The most important quantity is x, the generalized force. It is given as the negative derivative of the free energy of a system with respect to lambda, a process parameter. In the case of an isothermal reversible expansion or contraction of a gas, the generalized force is simply the ordinary pressure. If the process is thermodynamically reversible, then the total entropy of the universe remains constant. It follows that the sum of the generalized forces must everywhere vanish, and that in turn leads to the result that the sum of the free energies of the two components must remain constant throughout the process. This is an important condition that we will use in the no-go result. A common misconception about thermodynamically reversible processes is that they are merely very slow processes. That is not so. They are processes that are everywhere in thermodynamic equilibrium or minutely removed from it, and as a result, they are very slow. A process can proceed very slowly without being thermodynamically reversible. Sommerfeld's famous example is of a capacitor discharging very slowly through an arbitrarily high resistor. An even simpler example is of a balloon deflating very slowly through a minute pinhole. Both processes proceed very slowly, neither are thermodynamically reversible. A further important condition is that we shall consider thermodynamically reversible processes that are self-contained. This means that we will not allow interventions from external non-thermal systems. We saw an example of this type of external intervention in the isothermal expansion of a one-molecule gas. Some external agent needed to adjust the mass of the piston constantly in an effort to keep it in equilibrium with the gas pressure. That sort of external intervention by a non-thermal system is disallowed. Such non-thermal systems lie outside the province of thermodynamics. We will also preclude interventions from systems that are very far from thermodynamic equilibrium, for otherwise we should have to include consideration of the quantities of entropy that must be created in order to bring these systems into their far from equilibrium state. Here's an example. We take a very massive body, put it on wheels, and let its slow motion slowly compress the one-molecule gas. A very massive body like this, moving slowly in one direction, is very far from its thermal equilibrium state. Its equilibrium state is described by a one-dimensional Maxwell velocity distribution, so that at equilibrium it is nearly at rest, executing very slight Brownian motion. If we use it, we would need to take into account the amounts of entropy needed to bring it into the tail of the Maxwell velocity distribution. We now consider how to compute the probabilities of various thermal fluctuations. Take a canonically distributed system. Its system point will migrate through the system state space. The probability that it can be found at any point with energy E is proportional to the Boltzmann factor, the exponential of the negative of energy E divided by kT. The probability that a fluctuation will carry the system to a state corresponding to some subvolume V is given by the integral of this last expression. The integral is shown here. It is the partition integral restricted to the subvolume V of the phase space. We can associate a quantity of free energy with that volume of phase space by using the canonical relation shown here. What results is a very simple expression for the probability P that a fluctuation carries the system to some state. It is simply given as proportional to the exponential of the negative free energy of that state divided by kT. We combine these results to arrive at the no-go result. Consider any isothermal thermodynamically reversible process you like. Could be the expansion or contraction of a one-molecule gas, a detection process, or anything else. It doesn't matter. This characterization is general. The process will have some initial state, a middle state, and a final stage, and lambda is going to track our progress from the initial through the middle to the final stage. Since the process is thermodynamically reversible, we know that the free energies of all of these states must be the same. The free energy of the initial, the middle, and the final stages must be equal. We also know that the probability that the fluctuations carry the system to each of these three states is proportional to an exponential in the free energy of each of those three states. Combining these two results, we arrive at the no-go result. The probability that the system is in the initial, middle, and final stages are all equal. Fluctuations distribute the system uniformly across the entire process. That means there is no definite process with a beginning or an end. There's simply a muddle of fluctuations carrying the process to and fro. This is the process that we intended, a slow progress from beginning to end. This is the process we get. Fluctuations carry the system to and fro without any discernible beginning or end. Can we overcome fluctuations and bring processes to completion? Yes, but the cost is that we must create thermodynamic entropy by introducing thermodynamic irreversibilities. Let's calculate how much entropy we need to create. We overcome fluctuations by introducing a negative gradient in free energy over the process. We release the system in its initial state. We recapture it here in its most likely state. During the process, the free energy of the system changes by delta F cis. From it, using standard thermodynamic relations, we can calculate the net creation of thermodynamic entropy overall as the negative of that free energy change divided by temperature. The procedure described so far is not the most efficient because the system can still be found in undesired intermediate stages with some probability. We arrive at the least dissipative case by introducing a high free energy mountain over all of the intermediate stages. That makes it very unlikely that the system will be found in any of those intermediate stages. The system is released in its initial state and then captured in its most likely final state, and it is very unlikely that it will be found in any of the intermediate states. We can relate the probabilities of the final and initial states to the change of the free energies between the final and initial state, and then ultimately to the total entropy created in the whole process by the formula given here. Note that the probability attached to the initial state is not the probability that the initial state arises, but the probability that a fluctuation carries the system back to the initial state after it's been released from it. Rearranging the formula gives the final result at right. It tells us that the total entropy creation in the system has a minimum value that's given by k times the logarithm of O sub phin. The quantity O sub phin is the odds of the achievement of the final state, that is the ratio of the probability of the final to the initial state. Here's what this result means for molecular scale processes. Let's say we want to have odds of completion of 20 to 1, that is a probability of 95% success. To do that, minimally, we will need to create 3K of thermodynamic entropy. That quantity of entropy greatly exceeds the K log 2, that is 0.69 K of entropy that is tracked by Landau's principle. The result also applies to macroscopic scale processes. However, the quantities of entropy it requires are negligible at the macroscopic scale. If we want odds of completion of greater than 10 to the power of 10, it turns out that we only need to create 25 K of thermodynamic entropy overall. 25 K of thermodynamic entropy is macroscopically negligible. To get calibrated on this, consider the thermal energy of 10 nitrogen molecules, that is 25 kT. Here's the simplest illustration of these results that I can imagine. Consider a bead that can move frictionlessly along a horizontal wire. Each position along the wire is an equilibrium position. As a result, the sequence of positions adopted by the bead across the wire constitute a thermodynamically reversible process in which the bead moves over the wire. Consider the macroscopic case of a 5-gram bead. The no-go result says that the bead will eventually be uniformly distributed over the entire width of the wire. However, the timescales needed to achieve that distribution are enormous. The thermal velocity of the bead is of the order of 10 to the minus 9 meters per second. Huge amounts of time will be needed to achieve that distribution. It is quite different from a molecular scale system. Consider a bead of 100 AMU mass. That would, for example, be roughly an N-heptane molecule. Its thermal motions are large. The RMS velocity of such a mass is 157 meters per second at normal temperatures. As a result, its thermal motions will rapidly scatter it across the full width of the wire. We can overcome those thermal fluctuations by tilting the wire slightly, thereby letting gravity pull the bead down to one end. For the case of the macroscopic 5-gram bead, the amount of depression is minuscule. We need to press the wire by roughly 10 to the minus 7 Bohr radii of a hydrogen atom per meter in order to overcome fluctuations. This is an entirely negligible amount. It is quite different for the molecular scale mass, the 100 AMU mass, the N-heptane molecule. Even turning the wire vertical proves to have a completely negligible effect. This should not be a surprise to us. We know that N-heptane is a volatile liquid, one of the possible components of gasoline, and its thermal motions are fully able to fling it through an entire room. Merely tilting the wire does not realize the least dissipative case that we discussed earlier. To arrive at that, we would do something as is shown in the figure here. We would bend the wire so that the bead has to use thermal fluctuations to carry it over a large mountain that covers all the intermediate states. The case of the bead on the wire illustrates the basic processes at play. However, it is very, very simple. I have calculated more complicated cases elsewhere in a paper that I'll cite shortly. One process involves using an electric field to move a charge through a channel from one end to another. The second process uses a two-straight electric dipole to measure the sign of the charge of some target state. The thermodynamics of computation is based on an idea that is initially appealing and intriguing. It is the idea that there is some fundamental connection between information and thermodynamic entropy. That connection sounds initially implausible, but why not give it a chance? We've learned over the past century of all sorts of connections. Mass turns out to be energy, particles are waves, and geometry is gravity. So why not some connection between information and entropy? It's been over 80 years since Szilard made the first connection between information and entropy. As far as I can see, the connection has produced nothing but muddled theorizing. It is time for us to realize that not all intriguing proposals work out. Some simply fail. The connection between information and thermodynamic entropy is one of them. If you want more, please go to my website. There you'll find a research page that collects the various papers that I've written on this topic. The most recent and the most expansive is a paper that has just been published in the open access journal Entropy. It contains all of the results that I've described in this talk. You'll also find many of them in a discursive page on my website in the so-called goodies section. Thanks for listening.